Hello everyone. Today I am excited to share with you a transformative approach to teaching and learning mathematics, Constructivism. Our journey will take us from its theoretical roots to practical classroom applications, serving as a comprehensive guide for transformative teaching. Let's start by acknowledging a common challenge in many math classrooms, the traditional approach. All too often, it's a teacher-centered environment where students are passive recipients of knowledge. This leads to rote memorization of formulas and procedures without fostering a true deep understanding. As a result, the knowledge gained often remains innate, making it difficult for students to apply these concepts to solve normal real-world problems. This is where constructivism offers a powerful solution. It represents a fundamental paradigm shift, moving the focus away from simply teaching and squarely onto learning. Instead of being empty vessels waiting to be filled, constructivism empowers students to become the active architects of their own knowledge. In this presentation, we will explore how this philosophy can be effectively applied in the mathematics classroom, changing the way we teach and, more importantly, changing the way students learn.
So, what exactly is constructivism? To understand its power, we must first dive into its theoretical foundations, which are deeply rooted in the collective psychologies. Constructivism isn't a single theory, but a collection of perspectives built on the groundbreaking work of two key figures, G. Piaget and Lev Vygotsky. Piaget's theory of collective development tells us that children are not empty slides. They actively construct their understanding of the world by interacting with their environmental. They don't just observe information. They explore, experiment, and build knowledge step by step through distinct developmental stages. Vygotsky, on the other hand, emphasized the social nature of learning. Its social-cultural theory highlights that learning thrives through interaction with others, peers, teachers, and boarding culture. A key concept here is the zoo of proximity development, or ZPD. This is the gap between what a student can know and what they can achieve with guidance and support. This support, often called scaffolding, it is crucial for moving learning forward. Bringing these ideas together, we arrive at a core concept of constructivism, learning as act construction. This is a central idea. Learning is not a passive act of receiving information transmitted by a teacher. It is an active process where the learners take new information and integrate it with their existing experiments, beliefs, and mental fireworks. To build new understanding in essential, the student is not just a receptor of knowledge, but the subject, the architect of their own learning. Understanding its foundation is key, as it fundamentally changes how we approach teaching and the design of learning experiments.
Building on the theoretical foundations we just discussed, let's now explore the nature of mathematical learning from a constructive perspective. What does this look like in practice? It boils down to three key principles: active construction, situated learning, and social collaboration. First, active construction. Mathematical knowledge, whether it's complex concepts, a formula, or a proof, can't simply be handed to a student like a book. True understanding comes when learners actively engage in the process of learning, exploring, and reasoning. For example, understanding geometric properties isn't about memorizing a list of theorems. It's about discovering those properties through hands-on manipulation, drawing, and logical deduction. The learner must build the knowledge themselves. Second, situated learning. Learning is most effective when it's rooted in real-world context. Abstract mathematical concepts gain true meaning when they are connected to practical problems and situations that students encounter in their daily lives. This approach avoids the pivot of learning empty symbols and promotes a much deeper, more meaningful understanding. Third, social collaboration. Learning is inherently a social activity. It's through interactions and dialogue. This includes guidance and scaffolding from educators, but it also involves pure collaboration. When students discuss their ideas, explain their reasoning, and challenge each other's perspectives in group settings, they refine their understanding and correct misconceptions. It's through this social exchange that ideas are tested, changed, and solidified. Together, these three principles, active construction, situated learning, and social collaboration, create a powerful framework for meaningful mathematical learning.
Now that we understand the why behind constructivism, let's move to the how. How do we actually implement these ideas in the classroom? Let's explore some core teaching strategies and advanced instructional models. First, let's look at 4 fundamental strategies. Instead of lecturing, we must facilitate inquiry, design experiences that encourage students to discover knowledge for themselves. We must build on prior knowledge, connecting new concepts to what students already understand to create meaningful learning. We should implement a cooperative learning, structuring tasks that require students to work together, fostering deeper understanding through discussion. And crucially, we must value the process over the answer, focusing assignment on students' reasoning and strategies, not just the final result. This approach signifies a key shift in the teacher's role, from being the sage on the stage to the guide on the side, a facilitator who supports and scaffolds learning. Building on these strategies, we can use more advanced models. One powerful framework is the 5E instructional model. This cyclic model guides students through a complete learning journey, starting with engage to spark curiosity, moving to explore for hands-on investigation, then explain to formalize understanding, elaborate to apply knowledge in new situations, and finally evaluate to assess learning throughout the process. Another impactful model is anchored instruction. Here, learning begins with a realistic, complex problem, the anchor. Everything the students learn revolves around understanding and solving this authentic problem. This makes learning highly purposeful and motivating, as students see the direct relevance of what they are studying. Together, these strategies and models provide a concrete roadmap for creating a dynamic, student-centered classroom where deep, meaningful learning and truly flourish.
To make these abstract concepts more concrete, Let's work through a practical case study. Teaching the parameters of a rectangle using a constructivist approach. This example beautifully illustrates how zero translates into practice. We begin with step 1, engage. Instead of starting with a formula, we present a real-world problem. Our school garden needs a fence. How can we calculate how much fencing materials is required? This immediately contextualizes the learning, sparking curiosity and giving the task a clear purpose. Next is step 2, explore. We provide students with ruler and rectangular cutouts representing the garden. Their task is to investigate, to measure the sizes and experiment with different ways to calculate the total length around the shape. This hands-on exploration allows them to physically integrate with the concepts, building an intuitive understanding. Then comes step 3, explain. Students work in groups to share and compare their calculation method. They might discuss strategy like adding all four sides A plus B plus A plus B versus doubling the sum of length and width to multiply A plus B. This collaborative discussion is crucial. It allows them to articulate their thinking, learning from each other, and justify their approach. In step 4, elaborate. The teachers guide the class to synthesize their findings. Together, they move from their individual strategy to collectively derive the formula. Parameters is equal to 2 multiplied length plus width. Notice that the students are constructing the formula themselves, not just being told they. Finally, step 5, evaluate. To ensure understanding, students apply their newly constructed knowledge by calculating the parameters of various rectangular objects in the classroom, like desks, books, or whiteboards. This application in device context solidify their learning. This case study demonstrates the power of constructivism. By engaging, exploring, explaining, elaborating, and evaluating, we transform the learning experience from passive memorization into an active journey of discovery and understanding.
While Constructivism offers a powerful framework, it's not without its challenges. Let's address some common pitfalls and how to avoid them before concluding with its transformative power. First, a common misconception is that Constructivism means no more teaching, just exploration. This is a pitfall. It can lead to unstructured chaos. The correction is that Constructivism values guided discovery. Teachers must provide appropriate scaffolding when students hit a cognitive wall. It's about finding the right balance between letting go and supporting. Second, We often assume that group work automatically equals collaboration. This is another pitfall. Superficial group activities, where students work individually and just share answers, lack genuine intellectual exchange. The correction is to design tasks that require collaboration, like jigsaw activities or problem-based learning, while each member has a unique role and the group is accountable for their collective reasoning. Third, thinking that any task is a constructivism task is also a pitfall. Tasks that are too simple offers no challenge, while tasks that are too complex lead to frustration. The correction is to carefully design tasks that are just beyond students' current ability but achievable with guidance and collaboration. By navigating these pitfalls, we unlock the true transformative power of constructivism. It represents a profound shift from learning to know facts to learning to learn, a skill essential for the 20th century. It equips students with critical thinking, problem-solving, and collaborative skills, transforming them from passive learners into active, confident thinkers who truly understand and can use mathematics. Thank you for your attention. I believe in the power of this approach. We can create a generation of capable, lifelong learners.